I'm back with video number 2 for Unit 2. Did you guess the super scientist who was able to say BS on the law of conservation of mass? If you guessed Albert Einstein, give yourself a little pat on the back, call yourself a super chemist. So Albert Einstein, if you remember, was the guy who said that you can take mass and turn it straight into energy. And that's what the scientists in the Manhattan Project did during World War II when they started making nuclear weapons. It was because of Albert Einstein's research in converting mass straight to energy. So now I'm going back to Unit 2, okay? And the next slide talks about properties of matter. And properties of matter can be chemical. Where's my little thingy poo? There we go. Can be chemical or physical. And here's how you tell the difference between the two. If you don't chemically change the substance, it's a physical property. So if H2O stays H2O, it's a physical property. It only becomes a chemical property when you change it. So if I take iron and it rusts, it's no longer iron, it's an iron oxide compound, okay? So I have changed it chemically. I have changed the substance's identity. It's no longer just iron, it's iron with some oxygen added to it. So examples of chemical properties are how things react with air, acid, bases, water. One of my favorite is combustion. Combustion is a fancy word that super chemists use, and all it means is I'm about to blow something up, okay? It's about to go combust. So things like that, things that you blow up are kind of chemical properties. Physical properties, I'm not really changing the identity of it. And then those can be broken down into extensive and intensive properties. Do you change the amount of the substance? You know, instead of having 2 meters of copper, do I have 3 meters of copper? If you change how much substance, the amount of substance you have, it's called an extensive physical property. And I gave you some examples: mass, volume, length, shape. You know, I can have something like this and I can stretch it out and make a different shape. Intensive properties don't depend on how much substance you have. They are what they are and they never change. For instance, the first one over here under intensive is color. It doesn't matter if I have a little bit of sulfur or a lot of sulfur. It's a horrible bright color, okay? It's also a horrible smell. It smells like rotten eggs. If you've ever driven by a paper mill, chances are you're smelling some sulfur. Melting point, boiling point, it doesn't matter how much ice I have. Ice will always melt at 0 degrees Celsius. Water will always boil at 100 degrees Celsius. Doesn't matter how much I have, never changes. And density never changes. So ladies, if you think your man has given you a fake gold ring, you bring that thing to chemistry class and we will do a density analysis on it, just like we did in Unit 1 with those other metals, and we'll find out if your man is honest, okay? So those are my different types of properties. Now I want to talk to you about separating mixtures. And the reason I want to talk to you about this is in this unit, I'm going to give you a bag with a whole bunch of goodies in it. And you're going to have to separate out the iron, the sand, and the salt. And so some of these might be some technique you want to do when I hand you that lab, because I'm not going to give you a procedure. You got to figure it out yourself. So the first one over here is filtration. And I think that's common sense. Like I see a little funnel here. I see some filter paper in there. And filtration is really good if you have a kind of goopy, watery substance. Say you have some dirt and some water, you got some mud, and you want to separate the water out from the mud. If you use some filter paper and you pour your substance through, all of your dirt should stay up here, and all of your water, where'd it go, will go down there. Now, sometimes it's easier to decant a substance. So we'll do in a few units, we'll do a precipitation reaction where we take 2 liquids and bam, we mix them together and a solid falls out of it. It precipitates. It looks like it's snowing, but it's not snow. And that's why it's called a precipitation reaction. So if you have a substance like this, where you've got some solid down here and some liquid up there, you can try to decant most of the liquid off the top. And then you just heat this kind of wet substance on the bottom, and then you can weigh it. Alrighty, Pooh. Let's talk about some other ways to separate matter. I really like chromatography, and when I was a real super chemist doing research, I used chromatography a whole lot. I use thin glass chromatography, But you can also get a lot done with just paper chromatography. So you could say this is a beaker and this has some solvent in it depending on what you're working with. And this would be a piece of paper and you're going to do this. And you put your little dot or your little sample there and the solvent kind of creeps up the paper. And depending on how this chemical moves up the paper, you can identify it and say, well, yes, you know, this was the chemical I was looking for because this is what it should look like, or no, that's not the chemical I'm really looking for. We do a fun lab, the Who Killed Mrs. Fowlkes lab, and that's one of the ways you're going to identify the murderer. Dun, dun, dun. Next, we have electrolysis. It sounds like what it is. You take an electric current and you run it through a solution and it separates things out of it. In this case, I have some water in a solution down here and I zap it with some electricity and I get some hydrogen gas and I get some oxygen gas. Now, you guys should know hydrogen is very explosive. If you don't believe me, look up the Hindenburg, okay? Hydrogen is, okay? Distillation. So we are from Virginia, and there in the western part of Virginia, people are known as moonshiners, use distillation a whole lot. And distillation is a way of taking a liquid, and you might have a container that has a lot of liquids in it, but you just want one of those liquids, and you can pull it out of that solution based on its boiling point, because different liquids have different boiling points. And basically, where's my little thingy poo? You take your sample and you put it here and say, I'm trying to pull something off that's got a boiling point of 50 degrees Celsius. This, where's my little thingy poo, is the Bunsen burner heating it. And you usually have a thermometer somewhere up in here. And when it reaches 50 degrees or whatever the boiling point you want is, you take a flask and you start collecting it. And everything that comes off as 50 degrees is the substance you're looking for. And again, that boiling point changes depending on what you're trying to pull out of that solution. Okay, so you would have to look up the boiling point and collect it at that temperature. Centrifuge. If you've ever given blood or they've taken blood from you to test, you probably have seen one of these. It spins and spins in circles until all of the heavy chunks kind of fall to the bottom, so it kind of separates the solution. And the last example is evaporation. You know, if I have a saltwater solution and I want to pull that salt out of it, I can just heat it up and the water will evaporate or vaporize out and it'll leave me with these beautiful little white crystals. Maybe this might be helpful for your little labby poo, this unit. Hint, hint, wink, wink. So now we're kind of changing gears and we're going to talk about the periodic table. And you know, everybody comes into chemistry knowing a little bit about the periodic table because you have some really good middle school teachers who talk to you about it. And so the first guy that ever said, you know what, we're going to take these elements and we're going to put them in some kind of order was this fella over here that looks like Santa Claus. And his name is Dmitri Mendeleev. And he put the elements on a rough draft of a periodic table based on their mass. He said, you know, you're chunky, you're skinny, and he went skinny to chunky, and that's how he did it. He backed that mass up. Dmitri Mendeleev put his periodic table in mass. And it really kind of revolutionized our organization of elements. And then came this little fellow right beside him. Where's my little this guy right here, Moseley. And Moseley's like, you know what, Dmitri, you have a really, really good idea. But I think we should put it based on atomic number or the number of protons each element has. And the modern periodic table is set up like Moseley, according to atomic number, whereas Dmitri Mendeleev's is set up according to mass. Wow, that sounds like a really good test question. Okay, so the periodic table we're using and that we're familiar with is Moseley's. And if you look at it really hard, you'll find a couple of places where the mass actually goes up and then goes back down. All right, so the periodic table, oh, let me move my face. I'm up in the text. Okay, woo, there we go. So the periodic table consists of rows, and rows go this way, and columns go this way, okay? So rows are called periods, and they are actually energy levels, and the higher up you are, the lower your energy. And as you move down the table, the higher your energy level gets. So if you're on row 1, you're on energy level 1. If you're on row 4, you're on energy level 4, and you've got a lot more energy than those fellas in row 1. And it basically tells you how far the electrons are away from the nucleus. So those are periods or rows, side to side. Groups or columns are up and down, and we call them families because if you're in the same column on the periodic table, you share a lot of the same characteristics, like you're explosive or you're not explosive, or you have this many electrons in your outer shell. And I'm going to use that term a lot. Electrons that are in the very outer reaches of their atom, those are the ones going kapow, kachow, kapow, okay? The ones inside, close to the nucleus, they are sitting on the sofa eating a bag of chips watching the game. They're not going to blow up. They're not going to make pretty colors and fire. It's those outer electrons on the outside of the atom that are doing all the hard work, and they're called valence electrons. Oh, oopsie doopsie. No. Woo. Okay, there we go. So on this periodic table, oops, let me move myself again. Woohoo! On this periodic table, it shows you the difference between the metals and the non-metals. And what I really like about it is it has this staircase, and that's what we call it in chemistry. It's not even fancy, a staircase. To the left are your metals. To the right are the non-metals. And the substances that are on the staircase are called metalloids. And that means they act a little bit like a metal, a little bit like a non-metal. Except for aluminum here. Aluminum is always a metal, okay? It's a light metal, but it's always a metal. All right, let's see. Okay, properties of metals. Metals are good conductors of heat and electricity. They're malleable. Malleable means I can shape them or bend them into shape. If a person's malleable, you can bend them to do what you want them to do. They're ductile, which means you can draw them out into a long wire. And my personal favorite, luster. I like shiny things. I love metals. So the first group that I'm going to talk to you about in metals are the alkali metals. They are my favorite. If I had to pick a group or family, I would be an alkali metal because they explode. They're the most explosive, most reactive metals there are, okay? And their reactivity decreases as you go down this group. So as you get bigger, you're not as spunky, okay? You don't react as quickly. When they take a charge, anyone in this group will always take a +1 charge. And when you take a positive charge in chemistry, it means that you are losing electrons. So here I'm losing 1 electron. I have 1 valence electron, okay? So I can just give it away really quickly, and that's why I explode. And my personal favorite is they feel squishy like Play-Doh, but they are housed in big containers, glass containers of kerosene or diesel fuel, because as soon as they hit air, they explode, okay? So if you were to tell, I've touched it before, but my hand was down in a jug of kerosene touching something on the bottom. If you had a little piece of sodium, like in a lab, and you can't have that in high school labs, but you can take a little fleck of sodium and you can fleck it across the room, okay? And when it does, it explodes with the air right away. It's really, really pretty. And I like really pretty. Right beside them are the alkaline earth metals. They are the second most reactive, so not as cool as the alkali metals. They are harder than alkali metals, though. Those alkali metals I could squeeze with my hands like Play-Doh. You can still bend these, like we'll play with magnesium ribbon, but they look a little more like the traditional metal you're thinking of. They always look, first column takes a +1 charge, second column takes a +2 charge. So that means they're losing 2 electrons. It also means that they have 2 valence electrons. Now the metals, when I say metals, you're probably thinking of a transition metal. These are, silver, gold, nickel, copper, zinc, iron, that kind of stuff, okay? They are heavy. Mercury is the only one that's liquid at room temperature, and they all take multiple charges. So I can't say like this column is plus this and this column is plus that. There's only 2 transition metals that are consistent. Silver is always +1 and zinc is always +2. All right, I'm going to wrap it up for video number 2. Catch me in video number 3 in just a bit. Toodles poodles, see you in class.